Okay. All right, so let's go ahead and get back and get started. If you recall, what we were going to try and do was, start to tackle some of these limit state checks, and we've done cross-section proportion limits, and we've done the surface limit state, and then now comes the strength limit state. Now, I'm not going to lie, this is going to be a very involved check for a number of reasons. The strength limit state check for the positive bending region is going to be very simple, and we're going to do that tonight. The negative bending region, it's a little more involved, and it sort of deserves its own light in the sun. So I'm going to do that next week, okay? Because we have to assess local buckling, we have to assess lateral torsional buckling, and it's a little bit of an involved calc, and I don't want to rush it. But suffice it to say that comes next week. Also in the strength limit state, I guess specifically, is not just moment, but shear as well, and that's a whole other kit and caboodle as well. So I just wanted to sort of go back to, sort of fundamentals, where we're at and where we're headed, and then once we've finished all this, we'll come back and circle, constructability, fatigue, and what have you. So for the strength limit state, I want to start in the main body of the spec, particularly with Article 610.6. Now, if you skip ahead a little bit to 610.2, we're in flexure. Okay. So the nice thing about this is it pretty much points you everywhere that you need to go in terms of the spec. Now, if you want to know let me go up here so you know what page I'm on. I'm on page 6-135. So this is the section of the spec that relates to the strength limit state and particularly relates to bending. Okay, and we'll handle shear, of course, later on. Okay, so when you're dealing with a section in bending, you have to start off by classifying that section. Are you looking at a composite section in positive flexure? Are you looking at a composite section in negative flexure? Are you looking at a non-composite shape? And what have you. For starters, we're going to look at the positive bending region, and we're going to look at the bridge in its intact final state. So that is a composite section in positive flexure. When we're looking at the bridge during its construction process, when we look at constructability, we're going to be looking at non-composite shapes, and the capacity calculations get a little more funky, a little more hairy. Okay? But that's sort of another story for another day, particularly next week. Right now, I'm interested in a composite section in positive flexure. So everybody knows what I mean by that, a steel and a concrete deck acting together. Okay, so for composite sections in continuous or curved bridges, it's kind of cool that this works for curved as well, shall satisfy the following requirements. Now, in order to compute the capacity of a composite section, the spec requires us to determine whether or not that section is compact or not. Now, what does it mean for a section to be compact? Well, composite sections and straight bridges that satisfy the following requirements shall qualify as compact sections. Number one, the specified minimum yield strengths of the flanges do not exceed 70 KSI. Simple. Just don't use a yield stress greater than 70. That's easy. We're not using that. Our yield stress for our girders is 50, right? So we're good there. All right. Second point, the web satisfies the requirement of 610.211. Anybody remember what that was? That was just D over TW being less than 150, which we met that, right? So we're good there. Okay. Number three, we have to meet the following limit. So let's zoom in on this a little bit. Okay. We have to meet the following web slenderness limit. So this is a web slenderness. It's a D over TW. And it has to be less than or equal to 3.76 squared E over Fy. Okay? The only term that might be a little confusing is this one right here, this DCP. Okay? Now, if you recall from what we talked about a while back, D sub C stands for the depth of the web in compression. Okay? And D sub CP is the depth of web in compression at the plastic moment. Okay? At the plastic moment. So what I want to do is I want to go back to this. All right? Let me scoop this over a little bit. I want to look at this. Remember this calculation that we did together where we looked at MP for the composite beam? So here was the beam. We started off, we looked at the plastic forces inside all those sections. We figured out what case we were dealing with. We determined that the P&A was in the slab. Remember this, et cetera, et cetera. Everybody good with all this? Okay. Now, one of the things that we determined in this example, if you remember, is that the plastic neutral axis is in the slab. Remember, the plastic neutral axis was that sort of line through the section where all the forces in compression equal all the forces in tension. And we found that the plastic neutral axis was in the slab. I want y'all to think about that. Okay? Now, here's a diagram of that. So here's the plastic neutral axis. We found that it was in the slab. Specifically, we found it was what? 7.048 inches from the top. Been a while, but we did this calculation last time. Remember it? So think about that. Plastic neutral axis is in the slab. And what does that mean? It means everything above in compression equals everything below in tension. Okay? So this bottom flange, is it experiencing tension or compression? Tension. This web is experiencing tension. This top flange is experiencing tension. Okay? Now, let's go back to the spec. I'm asking about this quantity. DCP, the depth of web in compression at the plastic moment. But none of it's in compression, right? The whole thing's in tension. So what is D sub CP going to be, you think? 0. None of the web is in compression. So the depth of web in compression is 0. So this web slenderness limit over here, all this stuff on the left, is 0. And why is it 0? Because at MP, the whole web's in tension. Okay? Make sense? All right. That has to be less than or equal to 3.76 times the square root of what? 29,000 KSI over 50? What? I don't even need to do the math. I know it's going to work, right? Because I promise you 0 is less than a number that's positive and not 0, right? I don't need to do the math. So, for a section to qualify as compact, we have to meet 3 requirements. The flanges have to use a yield stress less than 70, which we do. Our D over TW has to be less than 150, which we meet. And we have to satisfy this requirement, which we do, right? So would you agree we have a compact composite section? Everybody okay with that? All right. Now, excuse me. All right. If you scroll down a little bit, it says compact sections shall satisfy the requirements of 610.7.1. Otherwise, it'll be non-compact and you use 610.7.2. Sound good? So let's start turning pages. So we turn pages a little bit. And we get to right here. Flexural resistance, composite sections and positive flexure. So at the strength limit state, we shall satisfy the following. MU has to be less than or equal to phi mn. Simple, right? Now, we've got this term related to lateral flange bending. Again, right now we're not going to consider wind effects. We can consider that later. But right now I'm really not worried about it. And you're going to see it's really really wouldn't significantly matter anyways. I think you can guess when you see the numbers. But MU has to be less than or equal to phi mn. Now, one of the nice things about the spec and the way it's been calibrated, phi for bending and for shear is 1. Okay? So it's simple. There's no, if you remember in steel design for bending, phi was like 0.9. Nope. Phi's 1 for the bridge spec, so it's a little easier. MU. What is MU? MU are our factored moments, okay? And we'll look at factoring those here in a second. M sub n, that's our capacity, which you all should be familiar with that terminology, phi mn, the capacity of a beam. Let's start off with the phi mn. That's simple, okay? Since we're in 610.7.1, the compact section, here we go. If dP is less than 0.1 dt, there's the capacity. Otherwise, here's your capacity. It's bilinear fit. Literally plug and chug. Okay? Sound good? All right. So what we really need to define are 3 things. MP, dP, and dt, and they are incredibly simple. Okay, let's start off with MP. We already did that, didn't we? Go through and go all the way down. Remember, we got MP was 64, 62.3. We already did that. Okay. Now, that's MP. dP. dP is the distance from the way tippy top of the section to where the P&A is. So, what is that? From the top of this section to the P&A, that was Y bar, which is, we already calculated, was 7.048. Sound good? DT is just the total depth of the whole section. Okay? So bottom flange, web depth, haunch, and then another slab thickness. Sound good? Pretty simple. It can't get much simpler than this. So I don't have a handout for this one because it's pretty short. So strength limit state. Composite, we'll say positive bending. So I'll say, for starters, by observation, section is compact. And we did that based off the following three observations. One, the flange yield stress was less than 70 KSI. Two, D over TW was less than 150. And three, 2dCP over TW was less than or equal to 3.76 square root of E over Fy. And we did that by recognizing that dCP is 0. All right. So if you have a compact section, we need three quantities. Okay? So I'll say, therefore, we need MP, which we already did that, and it was 64, 62.3 foot kips. We need DP, which is the distance from top of section, getting ahead of myself, to the P&A, which is 7.048, and then DT is total depth, which I trust you all can do that, and that comes out to be about 53.25 inches. Sound good? Okay. So here's how this works. First thing we need to calculate is dP over dt. Now that might not specifically follow what you're going to see, but I think it's a little easier to deal with, and that'll become clear here in a second. dP over dt is 7.048 over 53.25, and that comes out to be what? Let's see. Comes out to be 0.132. I trust y'all believe me on that one, right? So taking those two comes out to be 0.132. So I'm just going to pop the spec up real quick. So if dP over dt is less than 0.1, here's your capacity. Otherwise, your capacity is predicted by that equation, and it really is just plug and chug. So therefore, Mn is MP 1.07 minus 0.7 dP over dt, which is 62.3 foot kips 1.07 minus 0.7 times 0.132. See? Now we've already got that number computed. Plug and chug, and you get 63.93 foot kips. So if you want a behavioral observation why the capacity is a little reduced, the section is compact, but it's not super ultra compact. In other words, it's not able to achieve that massive amount of ductility required to hit. I get massive amount. It's not able to achieve the required amount of ductility to hit the full MP. So we drop it down a little bit. And AASHTO just uses this pretty simple linear relationship. It's basically just a y equals mx plus b fit to the lower bound of the data. It's pretty straightforward. Okay, so that's Mn. If we want to be technically we need to calculate phi Mn, but phi is 1, so that's still 15.93 foot kips. Sound good? Okay, so that's phi Mn. Now we need to determine our factored moments, right? Now, if you recall, we've already determined what the raw moments were right here. Remember, in our positive bending region, these are the worst case scenarios, right? This is the worst case MDC1, this is the worst case MDC2, DW, and so forth, right? So if I say, all right, now let's do factored moments. So we've got MDC1, and I'm just going to leave it in foot kips, so it's what, 702.74. I've got MDC2 is 146.08. MDW is 119.39. 9. And then our live load moment, using the positive value, is 1661.05. All right. Sound good? Now we need to take these moments and factor them. Okay. Now I'm factoring them according to the strength limit state. Excuse me. Specifically, strength 1, which strength 1 states that the load combo is 1.25 DC plus 1.5 DW plus 1.75 live load effects. Remember that? Sound good? So if I do that, I calculate the following. So I say, all right, let's take 1.25 times this plus 1.25 times this plus 1.5 times this plus 1.75 times this. And I go through and add that up, plug and chug, and that'll give me a value of 46.96 foot kips. Now I'm going a little fast, but is everybody okay with this? Does anybody have any questions? So to summarize, because I always like to put a little summary and make sure I understand what's going on. To summarize, we need our beam to resist a moment of 46.96 foot kips, and it is able to resist a FEMN of 6315.93. So are we good? Yeah, we're good, because FEMN is greater than or equal to MU. And if you want, you can calculate your design ratio, your performance ratio, and that comes out to be 0.657. Sound good? Now some of you might be thinking, well, wait a minute. You know, the positive bending region, it was fine in the strength limit state, it was fine at the service limit state. In fact, if you look at these numbers, it's not just fine, it's really fine. So why didn't we make that section smaller? In other words, if it's doing so well with this 14-inch wide top flange and the 16-inch wide bottom flange, why not make them smaller? Save on money, okay? And the answer is there's more going on, okay? We haven't looked at fatigue. We haven't looked at the constructability check. And I've mentioned this before, there are many cases where the worst loading condition that a bridge sees is while it's being constructed, okay? That's very possible, okay? We're not finished yet. But so far, the positive bending region's doing fine, okay? Sound good? All right. I actually think I'm going to call it tonight, because what happens next is looking at the negative bending region. And keep in mind, we're looking at the ultimate strength limit state. So we're assuming that concrete doesn't do any good at all, okay? So in that region, we got local buckling, we got lateral torsional buckling, and the equations get hairy, okay? So I would rather take my time with them. Sound good? All right, no homework tonight, but I will say this. Your design project will kind of creep up, so you might want to start to at least think about setting up your spreadsheets to where, you know, if you change some input, have it change and calculate as much output as possible. You know, your goal is to not do a single calc by hand in order to complete your design project. Just have your spreadsheet do it for you. Sound good? It's just something to think about. That's all I got. Y'all have a good weekend and good week. We'll see you on Tuesday.